Hi friends, in this class we will try to cover your yes your uh, module 1, that is column space of a matrix, then linearly independent sets and bases. Okay, first of all, the column space of a matrix. Column space of a matrix. We have a good discussion about what do you mean by a null space of a matrix. Similarly, you can define another subspace for a matrix, for another matrix, or for the same matrix A. For the same matrix A, we can define another subspace which is known as the column space of matrix A. And we will prove that how uh, you will be calling this column space of a matrix A. A matrix A is called as a subspace associated with a matrix. Okay, so a matrix A, we have two subspaces defined, that is, one is null A, and the second one is called A, or column space of A, null space of A, column space of A. So yes, here the definition of column space of an m by n matrix. A matrix A is of order m by n. The column space of an m by n matrix A written as col A is the set of all linear combinations of the columns of A. That means if A equal to A1, A2, etc. An, then call A equal to span A1, A2, A3, etc. An. Then I will A equal to A1, A2, etc. An. Then what are these A1, A2, A3, etc. An? These are vectors. For example, let me take an example for the example for A matrix A equal to some 5, 4, 3, then 2, 1, 5, 7, 8, 9, 10, 11. So this is our m by n matrix with m equal to 3 by 4. Now in the definition we have they have written as, the author has written as A equal to A1 to A2, etc. An of order m by n. So what are these A1, A2, A3, An? These are not the single real numbers. These are these vectors. These are A1, they correspond to this vector, A2 correspond to this vector, and etc. A1, A2, okay, A3 we will get this vector, then A4 we will get this vector. So these are vectors. So A1, A2, A3, A4 are vectors which is having a dimension, or which belongs to the set of all ordered triplet. That is, this belongs to A1 belongs to R3. A2 also belongs to R3. Similarly, A3 and A4 also. So in general, we can say that A1, A2, A3, right? A1, A2, A3, etc. An are belongs to or are vectors of R R 1, 2, 3 rows. So R m by n, if it is an m by n matrix, then m corresponds to the number of rows. So A1, A2, A3, the number of entries or number of elements in A1, A2, A3 will be the number of rows of matrix A. So A1, A2, A3 will be belongs to Rm. Rm. Okay, this is how you have to visualize the definition or what is written in this A or the you have to in this way you have to picturize this A matrix A. Okay, then the definition of column space says that call A is equal to span of A1, A2, etc. AN. Span we have already discussed. What do you mean by span? So what do you mean by span? Span means generation. You can say span of a matrix, or you can say generated matrix. You can also say like that. So span of A1, A2, A3, etc. AN. For example, span of uh, A1, A2, A3, 3 span. What do you mean by this? It means I will take three arbitrary real numbers. For example, P, okay, Q, R. I will take three arbitrary real numbers P, Q, R, where P, comma, Q, and R belongs to the set of all real numbers R1. So I will take these arbitrary variables P, Q, and R, and I will form a linear combination. Linear combination like this: P into A1 plus Q into A2 plus R into A3. Okay, equal to some Z, you can say, right? So this is what you mean by linear combination. So if you play with these P, Q, and R, you will get a different number of different Z. Z1 you will get for one set value of P, Q, and R, and another when you change this PQR with another value, then you will get Z2, right? Likewise you will get so many uh, Z1. Okay, Z1. Likewise you will get so many Z1, Z2, Z3, Z4, etc. Zn. You will get according to the values of Q when you vary this PQ and R values. Right now, I'm just giving some meaning to this Z1, Z2, Z3, Z4, and Zn. So can you say that these are vectors? Z1, Z2, Z3, Z4, and etc. Zn are vectors? Yes, you can say that these Z1, Z2, Z3 are vectors. Vectors. Why it is so? Because we have we have the linear combination PA1 QA2 plus RA3, right? Why? Because A1, A2, A3 are vectors of vectors. A1, A2, A3 are vectors which belongs to the which is a subset or which belongs to the set RM. RM. So okay, RM. Now this the dimension of what will be the dimension of this Z1, Z2, Z3, and Z4, etc. So yes, this P into A1, that this is again vector. Okay, a scalar number into vector will be a vector, and here also we will get a vector. Here also we will get a vector. So plus you if you add all the vectors, then you will get another vector that is Z1, okay, or Z2, Z3, Z4, etc. So what will be the nature of Z1, Z2, Z3? Z1, Z2, Z3 will belongs to R A, right or not? Yes. Okay. Now yes. Now I have called this as a subspace associated with a matrix, right? Null A is again a subspace associated with a matrix A, right? Similarly, the column space of A is also again a subspace associated with a matrix. Why? Because you can prove this. This core A is a subspace of matrix A. Subspace of matrix A. You can what can prove that by applying theorem 1. Theorem 1 says that theorem 1, when you go to this theorem 1, as theorem 1, that is, if v1, v2, v3, vp are in the vector space V, provided you have to imagine that these v1, v2, v3, vp are vectors. Okay, are in a vector space V. It can be ordered triplet or ordered quadrant, like that you have to imagine. Then span of v1, v2, etc. vp is a subspace of V. So the span of v1, v2, etc. vp is a subspace of V. Similarly, we are applying this theorem to this col A, this column space of A. Yes, this column space of A. Why? Because column space of A, col A, is span of A1, A3, etc. An. So that if you can write span of some vectors, then it is a subspace of the matrix A. You can say like that. Okay. Yes, since span A1, A2, etc. An is a subspace by theorem 1, the next theorem follows from the definition of col A and the fact that the columns of A are in Rn. Yes, the columns of A that we have already discussed, that the columns of A will be a vector which is having a dimension m. Okay. Now, next theorem, that is third theorem, is that based on column space. Okay. The theorem 3 says that the column space, okay, the column space of an m by n matrix A is a subspace of Rm. Okay, you have to make a correction that I have said a little bit earlier that the subspace of a matrix, I have said, right? Actually, matrix will not have a subspace. Matrix is just a matrix having definite entries, definite values of entries. For example, A equal to matrix of 3 by 2, A equal to 3 by 2, 3 by 2 matrix. Okay, 3 by 2 matrix, and 1, 2, 3. Okay, sorry, 1, 2, okay, not 3, 3, 4, 5, 6, right? 3 by 2 matrix. This is a matrix only. So you cannot define a subspace for this matrix. But the theorem states that, actually the theorem states that the column space, actually we have proved that the column space can be written as span of A1, A2, A3, etc. An. Right? Span of A1, A2, etc. An, we can write col A, column space A. Now, we have from theorem 1 that theorem 1 says that theorem 1 says that the if v1, v2, v3, vp are in a vector space V, okay, you substitute this v1, v2, etc. vp as a1, a2, a3, etc. an. Then are in a vector space V, okay, then span of v1, v2, v3, etc. vp is a subspace of V. That means span of a1, a2, a3 you have to find out. Span of a1 by according to this theorem, we are rearranging, we are resubstituting v1, v2, v3, etc. vp as a1, a2, a3, etc. ap, and we will show that it is a subspace of some vector space, So what is that vector space? The theorems here states that the span a1, a2 etc. an, where a1, a2, a3 etc. an are vectors of Rm. So obviously the span of our discussion, the vector space, our vector space mentioned in theorem 1 will be Rm. Right? Rm is a vector space. We have no doubt about that. We have proved already that Rm is a vector space. That is R. We have also generalized that Rn is a vector space. R1, R2, R3 all are vector space. So the A1, A2, A3 etc. An belongs to Rm. That is a will be an element of Rm, and then span of A1, A2, A3, An are subspace of Rm. Rm. That is the column space that is span of A1, A2, A3 etc. An. Okay, column space of an m by n matrix A is a subspace of Rm. It's a subspace of Rm. Now we are moving on to the example. That is, hope you understood. Moving on to the example. Okay, if you have any doubt, you can ask. We will have a doubt clear section also. Now, okay, with this example, you will get a clarity on column space of a matrix A. Yes, example is this one. That is, find a matrix A. Find a matrix A such that W is equal to column space of A. That means the examiner given the column space of A, that is W, and he is given W as W is equal to set of all vectors given by 6 that satisfy or given by 6a minus b. Then the second element of W is a plus b, and the third element of W is minus 7a plus 0b. Okay, this is our, and where such that a, b are real numbers. So this is the examiner given that the column space of A, W, and he is given this W. Now you have to rethink, you have to think in a reverse manner. That is, matrix A, we know that matrix A, let matrix A equal to A1, A2, A3, etc. An. Okay, where A1, A2, etc. An are the vectors that belongs to Rm. Okay, now A1, A2. Then we have the by definition we have the column space of a matrix A as call A is equal to span of set A1, A2, etc. This is our column space, right? That means span of A1. I'm considering this span of A1, A2, etc. I'm giving some meaning to this span. What do you mean by span? I will be considering some arbitrary real numbers. Let us say P. Okay, Q, R, R, S, and S, T, etc. Then span means P into A1 plus Q into A2 plus etc. plus some W into A, like that, right? That's where P, Q, etc. W belongs to real numbers. Okay, this is my this is what you mean by span of A1, A2, etc. Now this A1, A2, etc. ANR belongs to the columns of matrix A, right? Now our problem is this, that if you make, okay, this is the, given that column space, the examiner given W, so this is I'm equating equal to W. Now if you make this the given W, if you can write in this format, okay, then you will get some real numbers and columns or vectors, and those vectors you put together in a column manner, a1 a2 etc an, in a column manner, then you will get matrix A, right? So that is our way, our reverse engineering process, how it works. Okay, now I'm going to the solution. Yes, what we will do is this. I will take W equal to 6a minus b, a plus b. Okay, 6a minus b, a plus b. Now minus 7a plus 0b, right? And the examiner given as a b belongs to the set of all real numbers. Now I'm going to take this a and b outside, and this is will be equal to a into 6. First I will write the coefficients of a. In first element or first entry, we have the coefficient of a 6. Then we have the coefficient is in, for the second element we have the coefficient 1, and the third element we have the coefficient minus 7, right? Plus then, yes, b I am taking outside, b into, then yes, the coefficient of the first element, that is minus 1, then 1 second entry, then and that of third entry is 0. Right? This is our, okay, 6 1 minus 7. I will try to write it more neatly. That is a into 6 1 minus 7 plus b into b into minus 1 1 0, b into minus 1 1 minus 1 1 0. Right, this is our W, right? Okay, and this can be you can equate this to some p into a1 plus q into a2, like this, right? This is what you call span of a1 a2, where a1 a2 belongs to a1 a2 are the columns of a. So if you compare, we will get the matrix A is equal to 6 1 minus 7 first column, and the next column is minus 1 1 0. This is our matrix A. This is our answer, right? Okay, so that is what uh, the solution. Okay, yes. Okay, that is our solution. You can write this solution now. Yes, now another example. Let a equal to this matrix of order 3 by 4. Yes. Now if the column space of A is a subspace of Rk, what is K? That is the question. If the column space of A is a subspace of Rk, then what is K? What will be K? We have already discussed, right? Column space means you take these columns of A and you span it. Then what you will get? A resultant vector you will get. That vector will be having how many number of entries? 1, 2, 3. 3 number of entries. So they said, the examiner said that it is a subspace. You need not to check whether it is subspace or not. It is a subspace. It is understood. Then what is whose subspace? That is the question. Then K you have to find out. K will be 3. K will be equal to 3. Right? Now, if the null space of A is a subspace of Rk, then what is Rk? Yes. Similarly, we have null space means A into x equal to 0, set of all x values. Then we have 3 by 4 matrix A. Then for the matrix multiplication to be possible, the x order of x must be 4 by 1. So that means it is having four number of entries. 4 number of entries. So so set of all x will be having a 4 number of entries. So given that it's a subspace, so it must be a subspace of R4. So K is equal to 4. Okay, that's about our column space. Now I am moving on to the example 7. When the example, that is yes, this is given. This example is for your self practice. So you write down this example and practice this on your notebook.